In this video, we want to learn how to define a stochastic process. We will learn how to apply these definitions as well very quickly. So we define a stochastic process based on some of their statistics. And this it could vary from one application to another. So the definitions we need may be different. So in a stochastic process, we deal with many joint distribution functions. So because we have many random variables, so this is, let's say, time, and this is T1, T2, T2, etc. So you have, let's say, Tn. So you have n random variables. But this is not the end of it. We could have more samples. So if we want to define a stochastic process using the distribution, we have to write the distribution of infinitely uncountable joint distribution of infinitely uncountable random variables. And this is not practical. So this is why we could define the distribution of one sample. So this is one sample. So sometimes this is enough for some of the applications. So if you know the distribution of one arbitrary sample at time t is arbitrary, you may be able to solve your problem. In some other application, you may want to define the joint distribution of two samples. So the second one, we call it second order PDF. First one, you call it first order. Or you may need to take the distribution of n samples and so on. The thing that here we have to consider is that if you have the distribution of two samples, the distribution of one sample, is a marginal distribution of two samples. So, so fx t1 can be calculated from this one, and each of these, let's say, third order gives you second order. So they should be somehow consistent. Now, from the CDFs, you can get the PDF by getting the partial derivatives and so on. And so the consistency of these joint distribution shall be satisfied. Most of the application, you need only two of them, if not some of them. So another way to describe a stochastic processes is we can specify a number of some countable number of joint distributions for a random process. But the question is that if we describe that and then these PDF are consistent, that means that third order gives the second one gives the first one, and so on, is really going to be a random process which meets these joint distributions or not? And the answer is yes. So what we need is just to have the joint distribution. We don't need to worry about the existence. And there is a theorem which says that given a consistent finite dimensional joint CDF or PDF, there exists a random process described by these joint CDF. So this is why in this course and hereafter, you just need to describe your joint CDF or joint PDF, and you don't care about the existence of that. And we can extend these nomenclature of random process into multiple random processes, because in many applications, you're dealing with multiple random processes. For example, you can have two random processes on a probability space, and it means that the x of t is one random process, y of t is another random process. But however, we have some joint statistics of these two random processes. For instance, you take one sample from x of t at time t1, and you take another sample from y of t at time t2. And the probabilistic behavior of these random pair can be described through their joint CDF. For instance, you take n time samples, and then you will have 2n samples for x and y. So these joint CDF, this is the joint CDF of nth order joint CDF of these pair of random processes.